Welcome to chapter 7, part 2. Okay, we're going to continue our discussions of properties of expectations. And one very important concept that we're going to cover in this part is what we call the moment generating function. Okay, so might sound a little bit not sure what this is doing, right? It's generating moment. Okay, so now you might be wondering what moments are. Okay, so expectation is the first moment. Okay, and like expectation of like x, or where the random variable x is the first moment. And then expectation of x squared is the second moment. Okay, so you see that once we know those, if we know expectation of x squared, we can get the variance, right? Using our variance expression. So it is really useful, I would say, that we know what the moment generating functions are. So let's just dive into it now. So the moment generating function has a specific definition, okay? We write capital M and then parenthesis t. Okay, so that t is a particular value that you're gonna be using later when we're trying to get the expectation of x and expectation of x squared. Okay, so what we mean by that is that if you have a moment generating function mt, okay, of the random variable x, okay, t is actually defined for all kinds of real values, but it will be a particular t that we're going to use to get the moments later, is that mt. Okay, that's the function. So notice that here it's a function. Okay, it is a function about t at the end of the day. Okay, so what we mean by that is that, okay, so the moment generating function is actually defined to be the expectation of e to the tx. Okay, so t is what this t is. Okay, that's the same t. Okay, x is the random variable. Okay, so notice here, okay, if you're given what t is, then this whole thing, let me just highlight over here, okay? If you know, like say the random variable is x, okay, and t is just something, some quantity that given to you. In this case, we know that this is a function of x, right? So think about this as gx, as et, and then x, okay? So in order to get the expectation, naturally we have two cases, okay? When you have x with a discrete random variable, which is discrete random variable with PMF px, then that becomes, if you remember, right, it's gx px. Okay, so here is our gx. So you're looking at all of the possible sums, okay, at the sum of all of the possible x values where you're evaluating gx px. Okay, if you're having x as a continuous random variable, which you're given its PDF, then it's going to be an integral, okay, of this gx times fx dx, and then integrating on the entire real line. Okay, so what we are learning new this time is that we're defining what we call the moment generating function, which is actually an expectation of a function of x, okay? But then the moment generating function has this t involved, okay? So as you can see, t is actually the parameter for this moment generating function, okay? But at the end of the day, it's also related to the x that you're working with, okay? So this is the definition itself, okay? Like I said at the beginning, the moment generating functions can help us find the moment, okay? So here we know that all of the moments of x can be obtained by successively differentiating mt, okay, with respect to t, okay? And then you can set the result of t equals to 0 to get the moments, okay? So this sounds a little bit vague, but let's talk about the first two moments, because again, the first moment is the expectation of x. Second moment is the expectation of x squared, okay? So in that case, you can think of it as once you know the first two, you're able to get the variance, okay? All right, so let's do it step by step, okay? So like I said, we are going to get the moments successively differentiating mt with respect to t, okay? So let's first take the first order derivative, okay, which is the expectation, right, of t, e to the tx, right, with respect to t. So don't forget, t is the only random variable in terms of mt over here. So when we're taking the first order derivative, it is with respect to t, okay? So because of that, okay, what we're gonna do, as you can see over here, is that we're gonna move the differentiation sign into it, okay? And then the first order derivative with respect to t, so x is a constant, right? Because we're just doing it with respect to t. So this becomes the expectation of x times etx. Okay, so x is a constant and it's in front of t. So when you're doing the chain rule, you're gonna have this, okay? So once you get to this point, what's great is the first moment, okay, is by, like we are saying in this sentence, okay, you're going to take the first order derivative and then evaluate the m prime t at t equals to 0, and that will give you the first moment, which is the expectation. Okay, the second moment, okay, so we keep doing, so this is the second order derivative, okay, so we're doing, so now as you can see, this is the first order itself, so we're now taking the first order off the first order, okay, so we do it step by step, okay, just slow down, don't forget that this is a random variable about t, okay, this is function about t is the only random variable, x is a constant over here, that's why when you're using chain rules, make sure you're doing it correctly. Okay, so here again, you have a constant, right? And then another constant here. So if I'm doing the chain rule, this becomes expectation of x squared times e to the tx. Okay, and then of course, if we evaluate now at t equals to 0 for this double prime, we are getting the expectation of x squared. Okay, so in general, you might start to see a pattern, right? In general, you're gonna have the nth moment, okay, which is m to the superscript n, meaning that it's the nth order derivative. It's going to be the expectation of x and e to the tx, okay? And then if you set t equals to 0, then you're gonna get the nth moment. Okay, so this again is true regardless of whether you're working with a discrete random variable, whether you're working with a continuous random variable, right? Because as you can see here, what we are showing below the definition is generic, just looking at the taking the first order derivative, okay? But of course, for a particular distribution, if you're given, say, like x is continuous, which is like x is normal, then you're going to have a very specific moment generating function once you're taking into account of fx, okay? If you're working with, which we're going to look at the example, if you're working with x is a binomial, which is a discrete random variable, right? So all of this still holds, okay? But what you need to do, of course, is to actually get the moment generating function evaluated, you will have to use the PMF of a binomial in that case. Okay, so without further ado, let's look at that example. And the example goes this way. If x is a binomial random variable, n is the number of trials, okay, p is the success probability. So those are the two parameters for a binomial. Use the moment generating functions to obtain its mean and variance, okay? So just so you know, when we first covered binomial a few, I guess, I don't know, 5-6 weeks ago, the mean is n times p, okay? And the variance is np times 1 minus p, okay? And that's when we're back then showing it, not using moment generating function, okay, using the definition. But here, what we're trying to cover, again, because moment generating functions, as we know, we are able to get the moments, okay, by doing the differentiation and evaluating t at 0 to get the first two moments. So we should be able to get the mean and the variance in this way as well. Okay, so that's what this exercise is about. So the moment generating function, okay, generically, okay, is this, right? But then of course, now let's put it into the context of the binomial distribution, okay? The binomial, okay, so again, this is gx, right? So then the expectation again is sum of x from 0 to n, because n is the largest possible values of x, right? And then 0 is the smallest possible value. And then this is the gx function. Okay, so here we're using k and, oh yeah, actually, I will correct this when I upload this, but notice here, I think all of this should be k as well. Okay, so I'm using k. Small k is the value that x is taking, so I shouldn't have a small x here anymore, okay? Alrighty, so this is a gx function, okay? So it's e to the tk, okay? And this is the PMF of our old friend binomial, okay? N choose k, p to the power of k, and then 1 minus p to the power of n minus k, okay? So what we further do here is that, well, there are certain things we can collapse, okay? In particular, we can combine those two, because combine this p and e to the power of t, because both of them are raised to the power of k, okay? So we still have the summation going on, the choose function still stays. We have PET, okay, to the power of k, and then 1 minus p to the n minus k, which if you recognize the whole thing actually, okay, by the binomial theorem, it just becomes, so this is like, you can think of it as in the new success probability, okay? And then this is the order value, but more importantly, this is the binomial theorem, the A and B that we used to talk about in chapter 2 many weeks ago. And this becomes the sum of the two terms to the power of n. Okay, so this is very specific to the binomial distribution, okay? So the moment generating function, as you can see here, is this, okay? Now, to continue our work, okay, remember we're supposed to find the mean and variance. So remember, for that, we will need to take the first order derivative of mt with respect to t, okay? And the second order derivative of that as well. So when we set t equals to 0, we're able to get expectation and the expectation of x squared, okay? So let's do that, okay? All of this is just calculus, just be really careful doing this, okay? So again, when you're taking the derivative, don't forget that you're doing it with respect to t, okay? T is the only random variable here. In fact, if you look at this, if we take a moment to come back here, okay? X is gone, right? There's no X, there's no K, is already being taken care of, right? Because the expectation is supposed to take care of the X value or the K that we're using over here. So if you look at mt equals to this final, right? Final term, this is indeed a function about t, okay? So remember p and n, they're given to you, okay? So that's why when you're really working with the particular distribution, what you are having here, this is a function about t, so just take the first order derivative, okay? Which is, I'm not just gonna read this, but hopefully makes sense to you. Okay, this is chain rule again. Make sure that you're taking the first order derivative with respect to t. Okay, and then of course, if we do the second, it's just gonna get a little bit more complicated. Okay, so just bear with me. All of this should be correct, and then I will definitely recommend you to do it by yourself as well, just to make sure that the calculus works out for you. So I'm repeating those two lines at the top, so we can continue using these two results that we have done to get the expectation and variance. Okay, expectation we know is the first moment. Okay, so it's n prime when t equals to 0. So if we look at this, when t equals to 0, this goes away, right? And then t equals to 0, this is 1. So when you have p plus 1 minus p, so those two gets out as well, right? So you have 1 to the power of n minus 1, which is 1, and then times n times p. So that's why you have your expectation of np, okay? Variance, as we know, is expectation of x squared minus the square of the expectation. So if we do that, this is equivalent of evaluating the second moment when t equals to 0, okay? And then the square of the first moment, okay? So we need to evaluate plug in t equals to 0 here. So if you do it carefully, like a lot of those terms, as you know, because e to the power of 0 is 1, so a lot of terms got canceled. So in the end, I think you're gonna have n times n plus 1 times p squared plus np, and then you minus np squared, which gives you np times 1 minus p. Okay, so this is the variance, and we know the results before, the expectation and the variance of binomial from chapter 4, I think. And back then we're using definition to derive the expectation and variance. And in this chapter, we have learned the new technique of using the moment generating functions to do that, okay?